Hello and welcome to Mathematics Illuminated, where I shed light on any and all math topics from simple to advanced in a way that's easy to understand and interesting to learn. Please subscribe to my channel as I continue to post more videos and comment below on videos you'd like to see in the future. This is part 4 of a series I have on complex numbers. I'll leave a link to parts 1 to 3 in the description if you want to check them out. In the last video, I went over how to find the radius and angle or argument of a complex number, and in this video, I'll put that information to use. These are the topics I'll cover in this video. What is Euler's formula? How can we use the radius and angle of a complex number? And how can we put complex numbers into polar form and then back into rectangular form? Firstly, I'll go over Euler's formula. This famous formula is used for the imaginary constant in the exponent. It also uses the number e, which is Euler's number. If you want more information on Euler's number, I'll put a link to my video on it in the description. Euler's formula states that e raised to the xi power is equal to the cosine of x plus the sine of x times I. It can also be stated using theta instead of x, which, as we went over in part 3, is often used for angles. And since sine and cosine are used with angles, expressing the formula using theta is often better. In part 3, I went over how to define sine and cosine using right triangles. Here I'd like to go over another way to define them, a way I actually prefer. If a unit circle, which is a circle with a radius of 1, is centered at the point 0, 0, and theta is the angle with the positive x-axis of a line that intersects the unit circle at a point, the cosine of the angle is the x-coordinate of the point, and the sine of the angle is the y-coordinate. If that sounds complicated at first, don't worry, I'll be explaining it further. I'd also like to note that this definition works in any quadrant, and as I explained in part 3, the angles are going to be negative in the third and fourth quadrant, which recall are the quadrants at the bottom. With Euler's formula, this idea works the same way. E to the theta I power can be graphed as cosine theta plus sine theta I on the complex number plane. All of this information might seem quite random, but allow me to explain. I'll get straight to the point without any more elaborate explanation. Basically, any complex number x plus yi can be written as r times e to the theta I, where r is the radius of the complex number and theta is the angle. So let's take an example from part 3. Recall that we found the radius of 5 minus 3i to be the square root of 61 and the angle to be negative arctangent of 3 over 5. And so 5 minus 3i is going to equal the square root of 61 multiplied by e to the negative arctangent of 3 over 5i. This is called polar form, and it is incredibly helpful in different ways. First, I'll go into a bit of why this is true by demonstration. Notice I have Euler's formula in the top right for reference. Expanding polar form using Euler's formula gives that x plus yi is equal to r multiplied by cosine theta plus sine theta I. And expanding that gives this. Notice that we have both a real and imaginary term on the left side and a real and imaginary term on the right side. Seeing this, we know that the real terms are equal to each other and the imaginary terms are equal to each other. And so x equals r cosine theta and y equals r sine theta. Now that we know this, we can do some interesting things to this to show why it all works out. Squaring both sides of both equations gives this. And if you know some trigonometry, you know that cosine squared is equal to 1 minus sine squared. Expanding this, and seeing that these two terms are equal to each other, leaves you with this, which can be rearranged as follows. We have that x squared plus y squared is r squared, and remembering part 3 is exactly how the radius is defined. So far, so good. Now let's try something with the angle. We can write this equation since the numerators are equal to each other and the denominators are equal to each other. Then we can cancel the r out, and knowing sine over cosine is equal to tangent, we have that the tangent of the angle is equal to y over x. And remembering the ways angles were defined in part 3, we know that if you take the tangent of any of the angles, you get the corresponding complex number in terms of x and y. And so everything seems to work out just fine, like clockwork. If these explanations and all seem very abrupt or complicated, that's because I'm trying to convey this topic in a way that's able to be understood without an extensive knowledge in pure mathematics. And so I've decided to sort of just state the facts as they are and show why they are true, instead of giving a more gradual approach to proving they are true from scratch, which is significantly more complicated. The next topic I'll go into is an interesting example of Euler's formula coming into use. Expanding e to the pi I using Euler's formula gives the cosine of pi plus the sine of pi times I. And remembering that we're working in radians and that the cosine and sine functions deal with the x and y coordinates of the unit circle, we can see that the cosine of pi is -1 and the sine of pi is 0. Once again, I'd very much like to encourage getting familiar with working in radians, and getting familiar with the sine, cosine, and tangent functions. They're all very helpful, especially with complex numbers. We can see on our graph visuals that the angle pi, which is at the coordinate -1, 0, is how we get our sine and cosine values. Plugging these back into Euler's formula gives that e to the pi I is equal to -1, which is very interesting indeed. This special representation is called Euler's identity, not to be confused with Euler's formula, and it can be used to put any negative number into polar form. Recall that polar form is the radius multiplied by e to the angle or argument times I. Let's take -5 for example. It can be rewritten as 5 times -1, and using Euler's identity is equal to 5e to the pi I. And so this is -5 in polar form. Another interesting example of Euler's formula being used is when the angle is pi over 2. From the unit circle, you can see that the corresponding coordinate is 0, 1, which means that the cosine of pi over 2 is going to be 0 and the sine of pi over 2 is going to be 1. Expanding e to the pi over 2I using this gives that it is equal to I. And since the radius of I is just 1, that is what it is equal to in polar form. Let's try an example of putting a complex number into polar form and then putting it back into rectangular form. First, we must find the radius, which using the method from part 3 gives that it is equal to the square root of 3 squared plus 3 squared, which is the square root of 18, which can be simplified to 3 squared of 2. Noticing that our complex number is in quadrant 1, we can see that the angle is going to be the arctangent of 3 over 3, which is just the arctangent of 1, which is just equal to exactly pi over 4. And so, we now have our complex number in polar form, being exactly equal to 3 square root of 2 multiplied by e to the pi over 4I. Now let's try to undo this and put it back into rectangular form, to show that both forms are equivalent to the same number. Using Euler's formula, we see that we can expand this as 3 square root of 2 multiplied by cosine of pi over 4 plus sine of pi over 4 times I. Pi over 4 in degrees is 45 degrees, and if you're familiar with trigonomic identities, you know that the cosine and sine functions evaluated at this angle are both equal to the square root of 2 over 2. Multiplying this out, we get our desired solution, 3 plus 3i back into rectangular form. To summarize, we have Euler's formula, which is essential to memorize in the study of complex numbers. We have the definition of polar form, which one can derive by finding the angle and radius of the complex number, and we have Euler's identity, which is helpful for putting negative numbers into polar form, and is just a fascinating identity overall. And that brings us to the end of this video. Please subscribe to my channel, leave a like, and leave a comment on what you thought. In part 5, I will go over how polar form can be further used in the study of complex numbers. Farewell for now.